Hello everyone. Today we will be doing the new chapter, okay? And that is the turning effect of force. Now, this word we are familiar with, right? What is force? We know. What is force? The force is an external agent which tries to change the inertia of the body. That was the definition given by Sir Isaac Newton. We did it in class 9. Very good. Now, today in this chapter, we are very much interested on the turning effect. Now, turning effect, turn. You know what is turn. Let me tell you a very simple example. You can right now, you can observe that. In your room, there will be a ceiling fan which is rotating right now. And if you see to the ceiling fan up, you can see there is a rod which is attached to the middle of the circular base that a ceiling fan consists of, along with the blades. That rod is pivoted, is attached to the center of that circular base, and when we are switching it on, it is rotating around that rod. So that rod is not rotating, it is fixed, it is at rest, it is steady, but the lower base is rotating because it is free to rotate with respect to certain force which is coming. Why it is coming, I will do in later classes in magnetism, electromagnetism. Right now, just I am giving you a very simple example that you can see, and like I have drawn a diagram. This is a wheel and this is the axle of the wheel where the wheel is pivoted like this. Suppose this is the axle, you can attach the wheel here, you can attach the wheel here. So the wheel will rotate with respect to this axle, Can you see that? Good. Now when we are applying a force at the point where the wheel is fixed, then what will happen? The wheel will have a tendency to have a linear displacement, that is called the translatory motion. What did I say? Translatory motion. Sure. But if you are applying a force which is not applied to the point of where it is fixed, that is called pivot. P-I-V-O-T. Pivot. That time, since this force is applied not at the pivot, this F2, then what will happen? This wheel will have a tendency of turn this way, and that is we call rotational motion. Sure? So this is what we are going to do in this chapter. So force can have a translatory motion when it is not fixed at a particular point, it is free. But if it is fixed and you are even applying the force on that particular point, that is where it is fixed, then it will again show you the translatory motion, and this kind of motion we call slipping. You know, the skidding and slipping, what we say. You're riding a cycle, suddenly you apply the brake, then you will see your wheels, they stop, but they skid on the surface due to the inertia. That can happen. But if you are not applying the force at the point of pivot and it is fixed, the body is fixed, but you are not applying the force at that point of where it is, at the point where it is fixed, you are applying the force somewhere else, then what happens? The body will have a tendency to show you the turning effect, the rotational motion that we are going to do in this chapter. Sure? So let us continue with that. So here is the diagram through which I'll show you the turning effect of force. We have taken an extended body, you can see, with irregular shape, and you can see there is a point where it is fixed, and this point is known as pivot, as you can see in the diagram, and we have applied a force F at a distance, perpendicular distance D, with the line of action of the force. Okay, so please draw this diagram and I'll explain you the rest of the thing. So as I was telling you, we are now going to derive the expression for the turning effect of force, and this diagram is clear to you, I guess. Sure. So what is the turning effect? How we can calculate the magnitude of turning effect? And, in physics we always try to find out an expression by which we can calculate the different sort of things that happen around us, and that is what the physics is. We want to find an expression, we find a mathematical justification for that particular thing, why it is occurring and why it happens and how it happens. In physics we should know why and we should also know how. So that is what. So here, by definition of turning effect of force, we calculate the magnitude of turning effect. The magnitude of turning effect is called moment of force. I am repeating, the magnitude of turning effect is calculated by moment of force. Now, how we calculate the moment of force? We usually give a sign which is not given in your book. I'm just telling you. Just remember, the sign is tau. This is a Greek letter tau. Can you see that? Great. Now, what is tau, or what is the moment of force? It is equal to the applied force into the perpendicular distance between the line of action of force, like here it is like this, and the point of pivot. See, it is 90 degree. It is 90 degree. So this distance into the magnitude of force, these two should be perpendicular. If it is not, then we have to project a perpendicular line. Sure? Good. But in class 10, we do not have lines other than perpendiculars. You will always get something which is perpendicular to the force, so no worries. So what is that? Tau, moment of force, is a Greek letter. Tau is equal to force into perpendicular distance. Okay? So this is the expression by which we can calculate the magnitude of turning effect. Very good. Now tell me something. I'm telling you something which is very interesting. And what is that? We have this turning effect. Can you see that? And we have also seen the diagram, how it works, and everything is fine. But how it came is, right now in class 10, is beyond the scope of the syllabus. I'm not explaining to you. Just remember that turning effect of force, the magnitude is equal to force into perpendicular distance between line of action of force and the point of pivot, a point where the body is fixed. Clear? So eventually, when we have got to know a new quantity, the moment of force, we should know the unit. Now what is the unit? In SI, that you have to remember, it is nothing but Newton meter. Newton meter. Can you see? Newton meter. And in CGS is dyne centimeter. So these are the units. Okay. So this is the expression, this is the unit. Now, what is the very important and interesting part for this moment of force, or the turning effect of force, is that what are the factors that actually affect this magnitude of moment of force? The factors are obviously the force and the perpendicular distance between the point of pivot and the line of action of force. These are the two quantities by which we can calculate the turning effect, the magnitude of turning effect of force, which is known as moment of force. Now here, you see, suppose you are applying the force here. Suppose, okay, don't draw this in your class work. Suppose you are drawing a force here which is F dash. Now what will happen? What will be the turning effect? What will be the moment of force? The answer is 0. Now why it is 0? Because you are applying a force at the point of pivot. That means there is no perpendicular distance, there is no separation between the point of application of force and the point of pivot. Okay, there is no separation. Then what will happen? This body won't exhibit this rotational motion or this turning effect. You can see it will turn. This force will make it turn like this. But if you are applying here, there will be no turning effect. Why? Why it is so? Because you are applying the force at the point of pivot, and that is not causing any turning effect. So we need to have a separation. We need to have this perpendicular distance. Otherwise, there will be no turning effect. We cannot apply a force at the point of pivot or where the body is fixed in order to observe any turning effect. We have to apply a force at any other point which is not the pivot. That was I was telling you earlier in this class. So that is the thing. So two factors. The magnitude of force is very essential. More the force, more will be moment of force, more will be the turning effect, the more will be the rate of turning effect, and the perpendicular distance between the point of application of force and the point of pivot. So these are the two factors. In your textbook it is clearly written what are the factors which affects the moment of force. That factors I already told you. Okay, please write it down in your classwork and remember this. This may come in your school or board exam. So these are the factors which affect or which affects the turning effect or the moment of force. Now we can see certain example. Let us think about a steering wheel in a car or a bus or whatever. So how does it look? A steering wheel, it is having again the point where it is fixed, you know that. Suppose we have a steering like this, right? Okay, great. Now, in order to steer a car or a bus or whatever, what we do, we hold it here and we drive like this, isn't it? So this here is the pivot. You're touching or you're holding the steering like this. So here, when you are moving up, your other hand is moving down. Okay, so that you have a steering, or like this. So this is also turning effect, and this is also the moment of force. These are the examples. You can imagine about the key, right? We have locks. So what we do, we key in and then we give a turning effect like this, right? So these are the examples. In your book you will see a lot of examples like this. They have steering wheels, they have locks, they have ranges which is used to open the screws and all, screwdrivers. These are all examples of turning effect. In screwdrivers also we first attach the screw and then we rotate like this. You have seen, I guess. So these are all the examples of turning effect. Go through all these examples in your book. Okay, sure. So this part is clear, the factors, the units and how it looks and everything. We are moving into another section. Actually, you have to understand one thing. Previously, we were talking about force, its effects, turning effect, moment of force, units, and few applications and examples. I told you about the steering wheels, the lock and key, and everything. Okay. Now, when we are talking about a steering wheel, like again I have drawn here, not with the proper picture of steering wheel. I have just drawn a circle and how we hold the steering like this. Very good. So we hold the steering like this, and when we have to turn right, okay, so we do like this. When we have to turn left, my left, this side, we do like this. So this goes together, I mean both the hands. It's usually not safe to drive with one hand, like this. No, we drive it like this. Even for bicycles, for two-wheelers, we have two handles which gives me the articulation. Okay, so this balance is very important. So here it is. So we are applying two forces which are equal in magnitude in order to produce the turning effect. So we are using two forces. That is very important here. So we have drawn this diagram. Let's say if I take this line only, leaving other portion. So this line I have drawn here, AB, and the midpoint is say O. So we are applying two forces, F, like this, and this is called couple. Now why it is called couple, you can understand there are two forces. And these two forces are equal in magnitude but opposite in direction, but they are parallel. Can you follow me? So what is a couple? Two equal forces acting at an extended body on two different points, and their directions should be anti-parallel. Anti-parallel means since their direction, this direction is upward and this direction is downward, but these two are a set of parallel lines, so we call it in physics anti-parallel. I am writing it here, please copy it down. Anti-parallel. later in class 11 you will understand this more better. So this is the fact. So this one, we want to know the moment of this couple, like we did moment of force. Now we are interested in moment of couple. So how to do this? Can you see here we have the nature of turning is similar. I mean, this is what direction? This we call anti-clockwise. This is clockwise, like the clock rotates, and this is anti-clockwise. So this is giving us an anti-clock rotation. Fine enough. So what we have to do? What is the turning effect? The magnitude is force into perpendicular distance. Where is the pivot? The pivot is here. O. It is fixed there. So what is the moment of couple? Can you tell me how many moments we'll get here? We'll be getting 2, correct. We'll be getting 2 moments. One for this force, one for this force. Now with respect to which point we'll be calculating? We'll be calculating with respect to O because it is pivoted here. Every time we'll calculate with respect to pivot. Very good. So for this force, what is the moment? F into AO. This is the perpendicular distance. Plus, what is the other moment? For this, it is F into BO. So if I take all these common, what I am getting? AO plus BO. AO plus BO. What it is? AB. So finally the expression comes. Moment of couple. What is moment of couple? I am writing here. Please copy it. Moment of couple. It is force into. You can write it like this. So it is F into AB. What is AB? AB we call it. We have given a term. Nothing very difficult. What is called? Couple arm. Okay, we call it couple arm. So this is the expression for moment of couple. Force, either magnitude of either forces into the couple arm. That means this full. Now remember one thing. This particular derivation, it can come in your exam. They can ask you, show what is the moment of couple. Then you have to draw this diagram, you have to show all these steps, and finally you have to write this. The moment of couple is equal to force into couple arm. This word is very important. This is the key word for this derivation, couple arm. We call this distance by which the forces are separated, we call this distance as couple arm. Okay, sure. I'll come to the numericals, then you will understand it more better. Before going into the numericals, we have few more things to know that will come up now. Now we are very much interested about the sign convention. Why we are interested for the sign convention? And sign convention for what? Sign convention for the moment of forces. That's what we now want to know. Now why we want to know the sign convention for moment of forces? Because the force is a vector quantity and this perpendicular distance we are multiplying with the force. So finally the result which is yielding is definitely a vector quantity, and for vector quantity it is having direction. In order to identify, in order to understand the direction of turning effect, we have to understand this sign convention, and that's the reason why we have come to this particular situation that we should give some sort of sign convention so that we can understand the nature of turning effect. Now there already you have understood one thing. Just now I was showing you the particular steering wheel concept. So there we were observing that we can have an anti-clock moment, clockwise direction turning effect or clockwise turning effect or something like that. So in the general convention what we follow here, suppose we have an extended body, like we have taken a rod or something, it is pivoted here, we have applied a force like this, and we can see this force can definitely show a turning effect like this. So which is anti-clockwise. So we say the sign for the anti-clock moments of force is positive. And for this extended body, when we are applying force downward, what we can see, this will have a tendency to turn like this. So this turning effect will show that is clockwise. So in the direction of the clock. So this moment is, we give a sign which is negative. Suppose I tell you that there is a moment which is 50 Newton meter. So this, from this positive sign you can understand, okay, 50 Newton meter, that means the magnitude of turning effect is 50 Newton meter and the direction is anti-clockwise. If I write negative, then you can understand, okay, the magnitude is 50 Newton meter, but the direction of motion is clockwise. If it is positive, you can understand it is anti-clockwise. If it is negative, you can understand it is clockwise. So this is the significance of the sign convention. Okay. Now there are some descriptions regarding the concept called equilibrium of forces. Now what is equilibrium? There are two types of equilibrium. What are the types? One is called, I am writing here, you also write static equilibrium. I write EQB for short term, and another is dynamic equilibrium. So static equilibrium means, suppose a body is at rest and it remains at rest with respect to all the application of forces and other things we are applying on the body, but still it is not showing any change. It is not having any translatory motion, it is not having any rotational motion, nothing. So then we call it as static equilibrium. Even when we have dynamic equilibrium, suppose a body is moving with a certain velocity and it is moving, or it is rotating with that particular velocity, we are applying forces but nothing is happening to it. Then we call it dynamic equilibrium or equilibrium of dynamism. Whatever. Now, in order to achieve this equilibrium of a body, we have certain principles. Now, what are the nature of this equilibrium, or what are the particular characteristics of this equilibrium? First of all, in order to achieve equilibrium, we have to do two things. What are these? First, all the forces which are applied on the body, the resultant of all the forces, that means the sum of all the forces, should be equal to 0. That means it is not going to show you any translatory motion. I repeat, it is not going to show you any translatory motion when the sum of all the forces applied on the body is equal to 0. Great. What is the next part? The next part is here, that is moment of forces. Even suppose you have a body, say this book, you have a book, very good. This book, I am keeping it on my hand and then I am applying forces, it is not moving, so we can say that it is under equilibrium, but we are wrong. Why we are wrong? Because of the reason that this book is lying on my hand, I am applying forces, it is not showing any change, any translatory motion, nothing, so sum of the applied forces, the resultant is 0. Understood? Great. But what else? I can open this book like this. I can open. So this is what? This is turning effect. So when I am applying certain force on it, it is opening, it is showing turning effect. Alright, so this is not under equilibrium. Equilibrium means it will not show any change. It will be indifferent to the external agents, that is forces. It will not show translatory motion, it will not show rotational motion. But in this book, I was able to open the book, that means it is not under perfect equilibrium. Got my point? So what I am trying to exhibit to you is that in order to achieve equilibrium, first of all, sum of all the forces acting on the body, the resultant, it should be equal to 0. And second, the sum of all the moments which are there with respect to the forces which are applied on the body, that moment of force should be also equal to 0. Then only we can say, okay, the body is under perfect equilibrium. Sure, this concept is clear to you. Very good. So now we have a concept called principle of moment. Principle of moment. Principle of moment. This is very interesting, and it came from the concept of equilibrium only. Equilibrium says that algebraic sum of all the moments with respect to the forces acting on an extended body, it should be equal to 0. And if it happens, then what happens? There will be forces applied on a body which will exhibit anti-clockwise motion or turning effect. There will be some forces which will show clockwise turning effect. If this total anti-clockwise turning effect is equal to total clockwise turning effect, then what will happen? Anti-clock will cancel clockwise. So there will be no change. Great. This is the fact. There will be no change. That means the body is under perfect equilibrium. So what is principle of moment? What should we write? We should write, you can write it down in your classwork. We can write like this, that under the concept of equilibrium of extended bodies, under the concept of equilibrium of the extended bodies, principle of moment says that sum of anti-clock moment should be equal to sum of clockwise moments. Moments of forces we should write. Moments of forces, because in this case when you are applying this principle of moment, we usually don't see that one force or two forces only acting. We will be having more forces which are acting on the body, and if these two moments, anti-clock and clock, they are equal, then you are seeing net result is 0, no turning effect, and that is called the principle of moment. Okay, sure. Now I'll be showing you some experiment that you will do in your school lab for showing that particular experiment will show you how you can prove this principle of moment. That is very simple. Right now I'll show you that. Now this experiment that you are going to perform in your school lab, the verification of principle of moment, that is what we are going to do. So we will take a 1 meter long ruler scale, wooden scale you will have in your lab. So that is usually 1 meter long, marked 0 centimeter to 100 centimeter like this, and there will be a midpoint which is 50 centimeter, you can understand. So at 50 centimeter I'll tie a small string and I'll make it to happen from a rigid stand or from a particular point, so it will hang. So after a certain point of time the oscillation will stop and it will be straight. Now using two spring balance, I'll attach some spring balance at this side and I'll attach some weight W2, and this way the thing will tilt like this because it will going to show you the clockwise turning effect. And in order to balance it, I will apply some other weight which is known to me here at a distance say L1, and I'll try to balance this rule, this particular scale, the wooden scale. Until and unless then we are going to apply weights and try to balance this one. Balance means it will be again horizontal, it will not like this or not like this. It shouldn't tilt this way down or it shouldn't tilt this way down. It should be horizontal. Okay? So this way you can see this W2 is giving us clockwise, W1 is giving us anti-clockwise. What is the principle of moment? They say at equilibrium sum of all the moments in anti-clock direction is equal to sum of all the moments along clockwise direction in the turning effect like that. So we are now here only two weights, W2 and W1 and W1 and W2 like that. So what I am going to write, in order to have the clockwise, anti-clockwise, it is W1 into, since this is the point of pivot because I fixed the scale here, into L1, and that will be equal to clockwise. So that is W2 into L2. So we know what is the weight we have measured here, and also we know what is W1. So in this way we can actually verify the principle of moment when the ruler or the scale, wooden scale of 100 centimeter long or 1 meter long will be horizontal like this, it will be straight like this. Okay, so this way we can verify, and this is the fact that will be used in solving numericals. And while solving numericals, we have to understand, don't forget to write these arrows in order to indicate the nature of rotation, whether it is clockwise or it is anti-clockwise. Please don't forget it. Right now I am showing you another 2 problems so that it will be helpful to you, and will be going to complete this particular section, which is turning effect of force. And let us see few numericals right now. Okay, this you have understood? Sure? Okay, alright. Now let us do 2 problems. I have already written the problems one by and now we will solve. Please write down this problem. The statement of the problem goes like this. They have given a diagram. We have a 100 centimeter long meter meter rule, meter scale, and it is pivoted at the 50 centimeter mark, which is marked as O. You can see it is 0, 10, 40, 50, 60, 70, 80, 90 and 100 like that. So they have 40 gram force which is hanging or given at point 10 centimeter mark. So obviously when we are having this 40 gram force and they have asked in the question, this is the diagram given, and after this diagram they have asked that how we can balance this rule using 80 gram force placed at the other side of the pivot. This is the question, how we can balance the rule by placing 80 gram force on the other side of pivot. Now the first thing that we should start with, we have to first draw the diagram like this. Okay, great. Then we'll anywhere just write 80 gram force, and since when the 40 gram force was alone, it was having a tendency to tilt like this, so this is anti-clock, and when we are hanging 80 gram force, it will have a clock. So I don't know this point, so let us do like this. Let's say it is x from O. From O it is x, not from 0, mind it. So where is the pivot? At O. So what we have according to the principle, and they have mentioned how we can balance, that means how it can be under equilibrium, that means principle of moment. What does it say? Sum of the anti-clock is equal to sum of the clockwise moment. Very good. So what is the anti-clock moments we have here? What are? There is only one. There can be more. I can even hang another weight somewhere from 30, say 20 gram force. It can be a problem also, no issue. Don't worry. You just write on the left hand side, you just write all the anti-clockwise moment and add them up. And in the right hand side, you write all the clockwise moment and add them up. They are equal according to the principle of moment, and then only we can solve this problem. Sure? This is the third process. This is the way. Principle of moment. Sure? Good. Now let us proceed. So we have this 40 gram force. It is showing you the anti-clock moment. So 40 gram force into the distance, perpendicular distance. It is here at 10 and the pivot is at 50. So what I am going to write? I will write 50 minus 10. That means 40. I am showing this to the examiner that I have understood this is at 10 centimeter mark and pivot is at 50 centimeter mark. So the distance is 50 minus 10. Great. Now we go for this 80 gram force, and the distance we don't know, so we write x. We have to calculate this x. So what is it coming? 40 into 40 is equal to 80x. So from here we can easily calculate x is equal to 40 into 40 by 80. Sure? So what it will be? 20. So x is 20. Now this is not the answer. Please understand. This is not the answer. If you write, leave it here, 1 mark will be deducted. What you have to write? You have to write the exact position. So what is that? X is 20. From where? From O. What is O? O is 50. So what is the position? You have to write the answer like this. Position is equal to 50 plus 20, because it is 20 from O. That means 20 advanced from O. So 50 plus 20. So what is that? So what will you write the final answer? You will write that 80 gram force should be placed at 70 centimeter mark in order to balance the rule. Sure? You have understood? Don't forget these arrows. This will help you, and also it will send a message to the examiner that you have understood the logic correctly. Sure enough? Okay. Now here the diagram was given. Problem 1. Now come to the problem 2. Can you see problem 2? What they have given, a uniform meter rule, means 100 centimeter. You have to, think. Uniform meter rule. Meter rule means 100 centimeter. Can be balanced at 70 centimeter mark when 0.05 kgf is hung at 94 centimeter mark. Draw the arrangement and find the weight of the rule. So here the problem they have mentioned that the rule is balanced at 70 centimeter mark when 0.05 kgf is hung at 94 centimeter mark. So it is balanced at 70 centimeter means the pivot is at 70 centimeter. Can you follow me? Sure? Good. Let us draw the arrangement. Number 1. It will be done in this much place. It's very simple. Don't worry. So this is the meter rule. Let us mark it 0. Let us mark at 100. Good enough. We have 2 marks given. 70. So 70 will be somewhere here. So this is 70. Good. And here is the pivot. So this is the pivot. Because they have given balanced. Good. And 0.05 kgf is hanging from 94 centimeter mark. So somewhere here. So right here 94. Right here. Oh, okay. This is 70. This is the pivot. Can you follow? This is the pivot. This triangle means the pivot. So 0.05 kgf, direction clockwise. So this is the arrangement they have given, but we have not completed the diagram because we are missing one thing. Can you tell me what? We are missing the weight of the rule that they have asked us. Fine. Where will be the weight? This is another good question. The weight will be at the midpoint because it's a uniform rule. So midpoint will be the position where the weight will act. Now what is the midpoint? Is 50, and this is W, the weight, and this weight is giving it an anti-clock direction, and that's why this rule is balanced. They have given it is balanced. At 70 centimeter mark and 94 centimeter mark we have this one force, and at 50 centimeter we have weight. So this way it is balanced. It is under equilibrium. We'll be applying the principle of moment like we did in the last sum. So this diagram is over. Now we are going to solve. What we are going to do? We'll write W. This is anti-clock. So W into what is the situation? 70 minus 50. Again this I am showing to the examiner because he can understand, he or she can understand, examiner can understand, you have understood the logic. It is a pivot is at 70, weight is at 50, so distance is 70 minus 50. Great, equals to what I am going to write 0.05 into 94 minus 70. Sure, great. So what is coming? W into 20 is equal to 0.05 into how much? 24. So easily you can now solve this. Alright, let me do it here. This sum is already done, I guess. I'm just removing it from the board. I'll do the rest of the portion, because if I go below, you won't be able to see. Anyways, so what is coming? What is W? Is 0.05 into 24 divided by 20. Okay, so we can calculate this, isn't it? What is coming? 5 and 6. So 0.05 into 6, or 0.01 into 6. So what is coming? So what is the weight of the rule? W equals to 0.06. So this is the answer. You have understood the logic? Very simple. You have to follow the basic principle of moment. Sure? And you have to follow the markings, and that's why you can calculate the distances like this. 50 minus 10 or 70 minus 50, 94 minus 70. Every calculation should be done with respect to the pivot. This is the only principle, and do mark clock and anti-clock rotations. Okay? So this is the chapter. We have completed the chapter, and now it's your part. Sit with the book, study the sections, study the examples, study the definitions, study the principles that they have given, the nature of equilibrium and everything, and then solve examples that are there in your textbook. Do all the solve examples in your homework copy, and then solve the question answers, all question answers, and the numericals. You will mostly find numericals. So do all these things. Again, we'll come up with our doubts and queries in our WhatsApp group of AccentUs. Okay, so there I'll solve your doubts later on. So now this section, the force and turning effect of force, is over with these problems. Now it's your part to do the rest of the chapters. Do it well, study and do all the numericals and the question answers, solve examples and everything. Okay, so this is it, the turning effect of force. I hope you have understood this, and do subscribe the channel so that you can get the updates of the new videos which will come up for the next portion of force. Sure.